Okay, last video we were talking about using the Hermite polynomials and the wave function for describing harmonic oscillations. And so in that we have one quick little side note. I have drawn in the very teeny tiny top over here the wave function and how it crosses the boundary allowed by a spring. Sometimes it can actually go slightly outside the boundary. So if there's a probability outside of a boundary that the wave function can exist, that's called quantum tunneling. Ta-da! It's somewhat anticlimactic. And so I have a series of 1 page of notes, 38.8. Also Atkins goes into it, section 8.3, about a very close look at tunneling, in which you can see the attenuation or the transmission probability of the wave function through a boundary. So take a close look at that. All right, particle in a box, switching gears. Particle in a box gave us the principal quantum number. That's bound, the quantum number associated with energy states bound to a region of space. V is the quantum number associated with the vibration. M sub L, M sub S, and then there's an L also. Those are all also quantum numbers. And you had, at one point, had to memorize that if you have N, then you can have anywhere from 0 to N minus 1 L values, which represent the angular momentum. And for M sub L, it could go from minus L through 0 to plus L. All of those originate from the fact that these quantum numbers represent the set of numerical values which give acceptable solutions to the Schrödinger equation. So we need to have, for the hydrogen atom. Forgot to tell you that. The restrictions that we have, okay, not quite. The hydrogen atom doesn't have vibrations because we just have a single hydrogen atom. Anyway, the numbers that we're going to be gaining come from all of the different models that we're going to apply to different configurations that are like the hydrogen atom. Particle in a box, it's just what is the electron going to do when it's bound with no potential. Now what we want to do is we want to build more of these quantum numbers, fill in the gaps with M sub L, M sub S, which is your spin, and also L. So to start with that, let's revisit the Bohr atom. And that is simply, let's put it in the center. So you have your electron bound to a ring. So if the electron has wave-like properties, it must be a standing wave around the circumference of the wave, or of the region. So what that means is if we turn this on its side, if the wave function starts here, or if the wave-like properties, if they don't completely perfectly come back together, then you're going to have a slight offset. And if you think about what happens if you have a slight offset, well, you're going to have constructive and destructive interference. And if you go around enough times, you're going to have destructive interference such that your wave no longer exists. So the circumference, which is equal to 2 pi r, must equal to some integer value of the wavelength. But this wavelength for matter is going to be the de Broglie wavelength. So let me rewrite this. We've got 2 pi r is equal to n h over mv. So this is the de Broglie wavelength. And so let's see. So now I've got nh divided by m sub v. So I'm going to rearrange this a little bit, and I'm going to take mv and put it over to this side. So mv times r, and then take nh divided by 2 pi. So this is my angular momentum. And if I look closely, that's just equal to nh bar. Well, that's convenient. So now I'm going to introduce a different quantum number to where I have my angular momentum, now represented by j sub z, is going to be equal, instead of n, I'm going to call this m sub l h bar, where this m sub l is the quantum number for angular momentum. In particular, in the z direction. And what that means is it's going to be, if you imagine, let's go over here. So here's my electron, and it's going around the nucleus in this way. there's a z component, okay? And so as it's going around, there's going to be, if you take your right-hand rule, which is hard because this is going to be in a reversed image so you can see all the words I'm writing, but you take the right-hand rule and you take your electron and it's going to curl your fingers and push up that direction. As it spins around, there's going to be a component of its angular momentum, actually it's going to be going that way, and then there's going to be a projection onto the z-axis. Read Atkins. There's a wonderful picture of that to explain how that actual J sub z value is represented. Okay, so there are some caveats to M sub L. It has to go from 0, plus or minus 1, plus or minus 2. And also, I think that's all I have for now. So the way that I incorporate that into my wave function for the angular momentum of a particle on a ring, that gives me psi of theta is equal to e to the I m sub L theta divided by 2 pi to the 1/2. So angular momentum is quantized for the particle bound to a ring. Again, there's no potential here, but you'll also notice I haven't actually used a Schrodinger equation yet. You're just going to have to take my word that that's the wave function that you'll use.